Hello students, welcome, thank you, welcome back. We're going to continue today with Carbohydrates Part 3. Before we can start on before we continue with carbohydrates, I'll have to give you just a tad of organic chemistry to explain a few things. So let's go over a little organic chemistry. There are some structures in organic chemistry that you'll have to know to understand this. So let us begin here. This structure here, this molecule here is called pyran. So it's a six-membered ring with an oxygen. That's pyran. And so the reason I have to show you this is because some carbohydrates can be drawn in a pyran form. They can look something like a pyran, and I'll show you that later. And some of our carbohydrates, song is going off, will have a structure that looks like this. It's a five-membered ring with an oxygen in it. And this compound is called furan. So there's pyran is a six-membered ring, furan is a five-membered ring, and they both have oxygens in them. Okay. So, and I'm going to come back to this later when we start drawing some of our carbohydrates. Everyone okay with this one? Very good. Here, let's get another color. This structure here, in organic chemistry structure, can anyone tell me what this structure is? Something that has an OH attached. Anything that has an OH. An alcohol. There's an alcohol. Now, if we take our alcohol, and let's draw another structure here. R prime. Oh, wow. It's not responding. I hope it doesn't. Okay. Okay, can anybody tell me what this structure is here? So this is an alcohol because it has an OH. And this structure is an aldehyde. Now the reaction I'm about to show you occurs a great deal in biochemistry. And what happens is the electrons on the alcohol attack the carbonyl carbon. And so that's going to be a nucleophilic attack because the electrons, of course, are going to be nucleophiles, and they're going to attack the carbohydrate, or attack the carbonyl on the aldehyde, and then you're going to form this structure here. I should have drawn these different colors. I should have made the carbohydrate and the aldehyde a different color so you could see what comes from what. So I'm going to make the aldehyde green here. And this structure that we make is called a hemiacetal or a hemiacetal. So you have basically, for hemiacetal, you have an OR, an R, and an OH. And so this is a hemiacetal. Now, why is it called a hemiacetal? It's called a hemiacetal because it's not a complete acetal. So I'm going to draw a complete acetal here, just as a comparison, so you could see. And again, I don't want to do too much. Okay. Now if we put another, okay, we're going to still have our OH. But if this, I have an H here. Now, what I've drawn here, the blue one, it's still a hemiacetal. And so if you get rid of the OH and you put another alkyl group or something else, put another OR, this becomes a full acetal. And so this one has, so this has OR. It has two ORs, an R and an H. So that makes it an acetal. And if you only have one OR, it makes you a hemiacetal because hemi is half. Question?
That second, or when you replace it with that other R, does it have to be, because you have an R and you have an R?
I should have put this OR double prime. We'll put double prime. Yes, it's a different one. And so a hemiacetal has an OR, an R, and an OH. An acetal has two ORs. It's a complete acetal, and an R and an H. And so when your carbohydrate ring, when your straight chain of your carbohydrate closes and makes a ring, it goes from an alcohol to a hemiacetal. That's the ring structure. Okay. Now I need to show you one more. And so I'm going to put here ring so you'll know this is what the ring looks like. And the acetal, we're not going to really talk about an acetal right now. So I'm going to put it here an X because we're not going to talk about it. It'll be much later that we talk about the acetal. But the ring, a carbohydrate drawn in a ring form is a hemiacetal. And I'll show you that in just a second. Exactly, a carbohydrate in a ring form, right? If it starts out as an aldehyde, when it closes the ring, it becomes a hemiacetal. I hate to do this organic chemistry part because I know. Let me do this. Let me explain it this way. Let me just draw a straight chain carbohydrate, make a ring, and you'll see, oh, there's a hemiacetal. And that's going to be the best way. That's going to answer a lot of questions. So what I'm going to do here, I'm going to just draw glucose. So glucose is C. 2, 3, 4, 5, 6 H 2 OH. Okay, now I'm going to put my OHs. So remember, all I have to remember is 3 goes to the left, everything else goes to the right. OH, OH. But I'm going to make this one a different color. I'm going to make the one on 5 a different color. OH. Now here we have, up top, we have an aldehyde. I'm going to shade it so make sure we can see it. This is our aldehyde portion, correct? And now this OH, that's our alcohol portion. So what's going to happen, the OH on the 5 carbon is going to attack, or those electrons are going to attack this carbonyl. And so these electrons are going to go around and attack that carbonyl to make the ring of glucose. So we're going to go from the straight chain to the ring. So now we have an aldehyde and an alcohol, and we're going to convert that into a hemiacetal, and that's the closed ring. Question? Okay, so right now, for this glucose, we have here, this is the aldehyde portion. There's the aldehyde, and in glucose, we also have an alcohol portion, where we have lots of alcohols, but it's the 5-alcohol, the 5-OH that we're concerned with. The electrons on the 5-OH, let's give those electrons here. Those electrons are going to attack the carbonyl carbon. It's going to be a nucleophilic attack to close the ring of glucose and convert that aldehyde into a hemiacetal. And that's what I'm ready to show you now. I'm ready to close that ring up. Everyone with me so far? So, the way you want to think about it, the ring could close one of two ways. It could close going this way, kind of to the right this way, or it could close to the left going back this way. And so we're going to close it the red way. We're going to go back with the ring. Okay. And so when we do that, so this is going to be carbon. Let's make carbon 1 green. So I'm going to put carbon 1 right here. And this oxygen here, this red oxygen, I'm going to put the red oxygen right here. So now I'm going to just attach everything else. So that's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So if I numbered these over here, 1, 2, 3, 4, 5, 6. Okay, now I can connect everything here. And so carbon 1 is not going to be an aldehyde anymore. We're going to convert carbon 1 into what? A hemiacetal. And so this is an OR here. So, well, let me just go ahead and draw everything first. So we're going to have an H here, and then an OH. So I'm going to shade here. This is an OR. The yellow shade is an OR. The blue shading here is the second OR, or is the R. The blue is the R that's connected. And then the purple, of course, is the OH. And so now that's a hemiacetal. And so if you ever have a hemiacetal means that the carbohydrate ring has closed. So when the carbohydrate ring is closed, if the carbohydrate is an aldehyde or an aldose, then you form a hemiacetal. So this is CH2. I'm just going to finish the structure of glucose. Up, down, up, down. And so this is D-glucose. Can I just put GLC for glucose? Would you know that if you looked at these notes? Okay. And then this is going to be, this is D-glucose. But they're different. One of them is a straight chain. One of them is a ring. And there's a way we distinguish that. But I'm not going to do that distinction now. It's going to come up in a few slides. So both of them are D-glucose. One is a straight chain. One is a ring. And the ring form, in this situation, since it has OR, R, and OH, that functional group is a hemiacetal. Does that make sense? It's the same thing I explained before. This can be confusing. So I'm going to go back. I'm going to go back a slide here, and we're going to look at this in another way. If you have an alcohol, an OH can attack the carbonyl of an aldehyde to become a hemiacetal. And on the hemiacetal, you have an OR, an R, and an OH. Now if we go to glucose, There's our OH of our alcohol, our aldehyde. The OH is going to attack the carbonyl to give us the yellow shading is the OR, the blue shading is the R, and the purple shading is the OH. And so glucose in the ring form is a hemiacetal. That's the most difficult part of this chapter on carbohydrates. That's the part that biochemistry students most often get incorrectly or they don't understand. But it's really a simple concept. Everyone okay with that one? Okay. Now I'm going to do something else for you. You can also have this. You can have an alcohol. The alcohol can attack, I'm going to make this one a different color starting out, R prime, C, O, R double prime. Now, we noted this first molecule. What's this functional group? Anyone? That's an alcohol. Now, let's see if you can figure this one out. This is not an aldehyde anymore because there's not an H there. We've put another R there. Does anyone remember what the name of this functional group is? Say that again. A ketone. This is a ketone. This is a ketone. Now, just as before, the same thing is going to happen. The electrons on the alcohol are going to attack the carbonyl. And now, you're going to form this structure. You're going to have R, O, then C, R double prime, R prime, and OH. Now we call the last structure, when the alcohol attacked an aldehyde, we called it a hemiacetal. One of you can just figure this out because it makes sense. Listen to the question. When the alcohol attacks the aldehyde, we call the product a hemiacetal. But in this situation, the alcohol is going to attack the ketone. What is this product called now? A hemiketal, exactly. A hemiketal. So a hemiketal has two R groups, and a hemiacetal has one R group. A full acetal has two ORs, and a full. So what's the name of the structure? Let me just see if y'all can figure this out then. Okay. A hemiketal has two R's, an OR, and an OH. Okay, go back one. Go back two. A hemiacetal has one OR, one R. A full acetal has two ORs and one R. What's going to be the name of this structure that has two R's and two ORs? A ketal. It's a ketal. So when an aldose, when a straight chain aldose closes itself, it becomes a hemiacetal. When a straight chain ketose closes itself, what is it going to become? When a straight chain When a straight chain aldose closes, it becomes a hemiacetal. When a straight chain ketose closes, what does it become? A hemiketal. Name a straight chain aldose. Glucose. Name a straight chain ketose. That's a tough one. Fructose. Fructose is a straight chain ketose. I want you all to think about it this way. Fructose and glucose are brother and sister. They're brother and sister. What do you mean by that, Dr. Merida? Okay. And then I'm going to show you the straight chain structure of fructose before we close it up. So I'm going to draw glucose first. 1, 2, 3, 4, 5, 6. Okay, this is going to be glucose. And over here, 1, 2, 3, 4, 5, 6. This is going to be fructose. So glucose is CH2OH here, and then we have an aldehyde up here. And so for fructose, OH, OH, and only 3 is here, and then OH. So the structure on the left is going to be glucose. Now let's draw fructose. Every chiral center that's in fructose can be found in glucose. So for fructose is a ketone, or is a ketose. So you have your double bond O there. And so now everything else is the same. So here we have OH here, OH here, OH here, and CH2OH. No, the only difference here is for glucose, the carbonyl is on carbon 1. For fructose, the carbonyl is on carbon 2. That's the only difference. They're brother and sister. Glucose is the boy, and fructose is the girl. Okay? And so glucose and fructose, they're brother and sister. One of them is an aldose, one is the ketose. They have the same, the chiral centers, all of the chiral centers that are found in fructose are found in glucose. But the opposite is not true, because 2 is a chiral center in fructose, and it's not found in glucose. Repeat that question, please. It does. It has the carbonyl. This carbonyl has the highest priority. So remember, when you're numbering carbons, when you're numbering carbon chains, you give the lowest number possible to the highest priority carbon. So we could either number this 1, 2, 3, 4, 5, 6, or we could number it 1, 2, 3, 4, 5, 6. And so what we want to do is number it in a way that gives the lowest number to the functional group of highest priority. And the functional group of highest priority is the carbonyl. So it can either be 2 or it can be 5. But we want it to be 2 because that's the lowest of the numbers. So this is the numbering system for fructose. Yes. Well, it's not the fifth. It's the one. It's the highest. It's the highest numbered chiral center. And so 3 is a chiral center. 4 is a chiral center. 5 is a chiral center. And 5 is the highest chiral center. And so this becomes D. Because this is R. So this is D fructose. Does that make sense? And so the question was about, even in fructose, does carbon 5, do you still determine L and D by carbon 5? And the answer is yes. Any more questions? Okay, I have 5 minutes left then, because she's coming at 1 o'clock, right? Would I have time to just make a circle out of fructose? Would I have time to do that? No, I would be rushing. So we're going to stop there. We're going to stop there. If there are no more questions.